The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
And welcome. We don't think that purely performance-based specifications work very well for the transportation infrastructure. That's just our life experience. We think that if you're talking about performance-based specification where compressive strength is what you're looking for, very easy to do, not a big to do. If you're talking about durability, if you're talking about the transportation infrastructure, you're talking about bridge decks, you're talking about pavements, not very easy to do. First of all, there's very little even agreement within here, ACI, as to what you should specify. At least that's the impression I get. Okay, what are you specifying for cracking? What are you specifying for diffusion characteristics, permeability of the concrete? These are important factors for the transportation infrastructure. I have not found a concrete producer that does any research into this. I mean, and they shouldn't. I mean, why would they be interested in researching this? They're interested in producing concrete and making some money. So I don't know where they would truly respond to a specification that deals strictly with durability. So what I'm going to talk about today are two major jobs that we had recently. One was the reconstruction of the Goethals Bridge, and the other was the reconstruction of a major runway at JFK. First one I'm going to talk about is the Goethals. Now, we do not give mixed designs, okay? That we do not do. We do give mixed design requirements. We do put the concrete producer on a hook. We do hold them responsible for what he produces. We even have payment reductions in our contract if we don't get what we want within the PWLs we give, okay? But we do specify a lot more than what would be characterized as strictly a performance-based specification, okay? And why? Because our life experience tells us that we get a better job. So the Goethals Bridge was designed to have a service life of 100 years. Now, the bridge that it's replacing, the Goethals Bridge, is in existence for 90 years. The reason it's being replaced because of obsolescence. The lanes are narrow, we get a lot of accidents, so it's being replaced. The deck there is 90 years old. Okay, so when we talk about getting concrete to last 100 years, people chuckle, oh, nobody's going to be around, ha ha ha. Whether it lasts or doesn't, who's going to know about it? Well, you know what? It's not a big to-do to get concrete to last 100 years. There's a lot of concrete out there that lasts 100 years. The sad part of it is that a lot of the concrete I see produced today, I wouldn't give you 2 cents whether it would last 100 years because of some of the nonsense we pull. Okay, you go out there, you don't have to be a concrete expert to say, you think this is going to last 100 years? Are you kidding me? But that's what we do. Now, how do we get concrete to last 100 years? Talk about a bridge deck. Bridge deck in the Northeast. A lot of de-icing chemicals, chlorides. We can't allow the chlorides to get to the steel. If we do, we're going to reduce the service life of that deck. Now, how do we predict a 100-year service life? Well, we got these programs, ACI Life 365, right? Stadium. And what is it based on? Mostly diffusion characteristics and cover to the rebar. But you know what's interesting? They all ignore cracking. Cracking is not part of the equation. Everybody, I think, assumes, this is the impression I get, there are no cracks in the deck. Has anybody gone up and seen one of these decks? Most of them have a lot of cracks, more than you would ever want. So how do we as an industry accept this as a design methodology? When I question people on this, the line that I got from the engineer of record was, hey, Kaz, get with it. This is the way we play the game. Well, that's not the way we play the game, okay? I think that when we design mixes for bridge decks, one thing that we have to pay attention to is putting together a mix design that has the lowest potential for cracking. I'm not suggesting that for a bridge deck, you're not going to get any cracks. But for God's sakes, we could do a lot better than what we do. Some of the mixes that we put together are destined to crack. And we do it over and over and over. And, you know, a lot of it has to do with poor mix designs, and we blame it on the contractor workmanship. It has nothing to do with workmanship. The stuff that we put together in that mix didn't stand a chance of working. Okay, so number one, I think we got to put mixes together that have a low potential to crack and have low permeability. Of course, freeze-thaw durability is not a big deal. Put a little air in it and you're good. How do we build life experiences into performance-based specifications? There are things that we've come to know through working in the industry for 30, 40 years that we found that work and others don't work. It's not that easy to put it in a performance-based specification, okay? It's not, okay? So we say certain things there. You will not do this, you will do this, and you will not do this. They're not just arbitrary decisions that we make up just to break the contractor's, you know what. We put them in there because they work. Okay, how we put it in an ASTM specification might be a little difficult. So here's the specification for the Goethals Bridge. Now the Goethals Bridge was a 3P job, private-public partnership. However, we did have enough of our specification in there to exert some leverage on the contractor to give us what we wanted. The prime contractor there was Kiewit, and in my opinion, Kiewit is a very good contractor. Okay, and we had what they describe as concrete wars. I don't think they were that bad. I thought they were discussions where we were talking about the mix designs and what to use. One requirement that we had on our spec was you will use 1.5-inch aggregate. Now again, people say, well, you shouldn't do that. Well, you know, we have found through the years that the larger the aggregate, the more coarse aggregate you have in there, the less cracking you get. I mean, this isn't something that we need to research too much anymore, and yet there is a great reluctance to do this. This turned out to be an unbelievable wrestling contest with the contractors. He didn't want to do it. And he didn't want to do it because difficulty in pumping 1.5-inch stone, difficulty in finishing it, difficulty in consolidating, all of them turned out to be not true. Okay, when all was said and done. And we did use 1.5-inch aggregate. I think we could have used more stone in it than what we have, but I'll show you the mix design. Water cement ratio 0.4 or less, well, that's standard. As Colin showed us, that's nothing new. Shrinkage requirements. Now, Colin said we should provide shrinkage criteria if that's what we want for mixes that have a low shrinkage potential. You know, and again, that's not as easy as it sounds, okay? You have 157, you have the ring test. How do you do the 157 test? You know, do you follow ASTM 157 to the T? Well, if you do, I'm not quite sure what you're getting, okay? So in our specification, we say you strip it in 1 day, and after 1 day, you get the initial reading, and then you dry cure it for 28 days, and that's how we want you to measure shrinkage. One thing we found when we even with that, which is more stricter than what ASTM has, when we were having bridge decks with, we used to use silica fume, we don't anymore, and we would get a lot of cracking in the silica fume mixes. And when we follow this standard, the silica fume, the slag, the fly ash mixes all exhibited the same shrinkage value. All the same. We said, well, how is this test worth anything? How come in the field there's so much difference that the silica fume exhibits so much more cracking? So I said to my colleague in the concrete lab, I said, do me a favor. Let's try to measure the shrinkage as soon as you can strip that prism without damaging it. Let's see what we get. He did that. And he stripped it in 10 hours. And we measured initial shrinkage from 10 hours on out. The shrinkage went up 40%. Now, do we all do that? No, we don't. You know, that's when we found, wait a minute, what is it with the silica fume? Do we really want to use this stuff? And of course, the conclusion we came to, we don't want any part of it on our bridge decks. You want to put it in a little high-strength concrete, go right ahead. I'm not quite sure what the silica fume buys you in a bridge deck other than guaranteed cracking. So that's our shrinkage requirement. Rapid chloride permeability test. Okay, that's what we use for acceptance criteria for bridge decks. And what was interesting when we got in on the Goethals Bridge, the reluctance to do this test during production, that we should just do this test once for the mix design, hold it in our hip pocket, and assume nothing's changed. And I said, well, if we do that, let's not do any testing. You know, if you believe that people are going to tell you when anything's changed and you don't do any need to do any testing for diffusion, which is the primary factor for the longevity of the deck, why are we making cylinders for compressive strength when we don't have a problem with that on none of our jobs? So make a long story short, they would say, oh, this costs a lot of money. Well, I don't give a hoot about how much money it costs. You're going to do it. And we did samples for the rapid chloride permeability test every time we made cylinders. For every sample we did that, okay? And that's the way the job went. 6,000 PSI concrete, not a big deal. The other thing that we again, Colin Lovell said we shouldn't do this, we did. You must use type F fly ash, okay? Now, why? We didn't do this just to be arbitrary. We found through the years that for bridge decks, structural decks, we get less cracking when we blend fly ash with cement. We get less cracking. The most cracking we got is when we use silica fume. It was horrendous in general. Bad, not good, terrible finishing, terrible cracking. Then we went to slag. Slag produced some cracking, not as much as silica fume. We found we got the best results with fly ash. How do we build that in a performance-based specification? How do we do that? We know it works better, okay? So how do we do that? And again, I'm entertaining suggestions. We're willing to listen. The other thing that we said, absolutely no silica fume. There was a consultant hired on this job, and they came in and they said they want silica fume. Okay? So we went round and round and round and round, and we finally agreed that we wouldn't use silica fume. The engineer of record called me a while ago, and he asked me a question on a job that he had, and he says, you know, Kaz, he says, you made a believer out of us. On all our jobs now, we don't use silica fume, we just use fly ash, because we agree with you, it does seem to work well. And he says, you know, I still remember your words when you used that profanity. I said, I use profanity? I can't believe that. He says, yeah. He said, we were debating this for 2 or 3 hours, and you said, that's it? There's no way we're using freaking silica fume. And he said, and that ended the discussion. And I said, oh, I don't remember that. I said, I can't believe I used that kind of language. But anyway, we did not allow silica fume in the bridge deck. And again, I kept asking, well, what the hell do we need it for? Give me a good reason. I never got one. So anyway, we talk about how do we spec shrinkage. Colin said, spec it. All right, here you go. Here are the tests. Here are the two that used in the industry. C157, maximum size aggregate, 2-inch. I'll show you the JFK runway. We have up to 10% aggregate retained on a 2-inch sieve. Does it make a difference in the shrinkage test if you have 2-inch aggregate? I think it probably does. So is this a good indication of shrinkage? The restrained ring shrinkage test, maximum size aggregate, a 1/2 inch. If all this is supposed to do is give you an indication of the paste shrinkage, then maybe it's worth something. Diffusion, ASTM 1202. Again, we decided to go to a accelerated test because nobody wants to wait 90 to 120 days to get Coulomb numbers below 1,000. Now, if you stick with the 28-day requirement for 1,000 coulombs, then you're going to have to put up with accepting silica fume or metakaolin. So we said, well, there's no way we want that. So we went with this accelerated test, and we do this on all our jobs now. 7-day curing at room temperature, 21-day curing at 100 degrees, and people say that that should mimic the life of that concrete in 6 months. I don't know if it does or doesn't, but when we've cored concrete in place, even on this Goethals Bridge, 6 months, a year out, for whatever reason we had to take cores, the Coulomb counts on those cores were always less than 500. Okay, so this is not a bad test to give you an idea of how impermeable that concrete is. So Coulomb counts below 500 are pretty damn good in my book. Okay, so here are the requirements for the Goethals Bridge deck. 6,000 PSI concrete, shrinkage in 28 days. Coulombs, again, the accelerated test, less than 1,000 in 28 days. And you had to use 1.5 inch aggregate, no ifs, ands, or buts. Here is the mix design that we got. Now, I don't think this is the best mix design in the world. You have 625 pounds of cementitious material. I don't think you need that much, okay? But, you know, we're trying to push the bar up. I think you could probably get away with 550 and meet strength requirements and meet everything if you graded the aggregates properly. And that's another, veil of tears, getting the concrete producers to blend aggregates. Now, people talk about, well, you know, in urban areas, we don't have the room to set up bins for aggregates, so that's why it's difficult to blend aggregates in New York City. Well, you know, every asphalt plant in New York City has 5 or 6 bins for blending aggregates, because in asphalt, if you don't blend, you're not going to get asphalt that's going to stand up to any kind of traffic. So I think we haven't done it in the concrete industry because we didn't have to do it. But if we really want to produce concrete that's more durable, less prone to cracking, blending aggregates is certainly the way to go. It's the most economical way to go. And hopefully the industry goes in that direction. So anyway, here's the mix design. Type F fly ash, 25%. We wanted 30%, so we had to give the contractor something. For whatever reason, they wanted 25%. We said our experience is 30% works the best. They wanted 25. We said, okay, go to it. Water cement ratio 0.37, air content, and Delvo. We wound up putting in 18 ounces of Delvo. And it's interesting, I was against putting in that hydration control admixture because of fear that someone will overdo it and the concrete will sit on a deck for 24, 48 hours, and then you're going to have a lot of cracking. But when working with Kiewit, they showed us, we had mock-ups, and we just couldn't finish it after 60 minutes. 60 minutes after the water met the cement. And the concrete was kept below 75 degrees. If the concrete was higher than that, we would substitute some ice for the water. We kept the temperature of the concrete below 75 degrees. And Kiewit was very good at doing that. And yet we couldn't get the right finishability to that concrete after 60 minutes. When I called up the cement supplier and I said, what the hell do you got in this cement? He says, well, you must have a hell of a lot of cement in there. I said, we have 470 pounds. Well, that's not a lot. How come you're having a problem? I said, we're having a problem. We can't finish this after 60 minutes. Oh, that's impossible. I said, Paul, it's not. We have a problem. He called me back and he says, yeah, I talked to the contractor. He says he does have a problem. I said, that's what I told you. My point here is that nobody else had a problem. Nobody else ever called the cement supplier that they couldn't finish this concrete in 60 minutes. We couldn't. My question is, if you put in now a corrosion inhibitor without set control admixture, now how do you finish this concrete? If you put 40 pounds of silica fume in this concrete, how do you finish this concrete? It's bad enough we had 475 pounds of cement in this concrete, and we had a hell of a time finishing it, okay, without putting the Delvo in. So, we put some of these things in these concrete mixes that make it very difficult for the contractor to finish. We've worked with some of these mixes with the fly ash, with the fly ash and the silica fume and the corrosion inhibitor in there. It's a job for the contractor to finish it. And again, you might have concrete that has a very low permeability, but if you've got cracks every 6 to 10 feet, what have you accomplished? I don't think you've accomplished anything. So again, this is the mix that we used, and it turned out very good. Here are the results. Compressive strength, 56 days, 8260. As I said, I don't think we needed the 625 pounds of cementitious material. If you just extract how many PSI we got per pound of cement, we could have taken out 75 pounds of cementitious material, and we would have been at 7,200 PSI. So we certainly don't need all that paste in there. Again, more paste, more potential for cracking. If you're talking about bridge decks, you want to reduce the amount of potential you have for cracking so that you don't give a direct conduit for water to go through a crack right to the rebar and start the corrosion process from day one. And there was the water cement ratio that we actually got, and that's the other thing that we do, okay? We do use the microwave test in the field with every sample that we take to determine water content, and people say that test method doesn't work, it's whatever. There's several stories out there. We've been using it for 20 years, and it does work. Okay, I was talking to an engineer from Europe. He said that they have a test in Europe similar to the AASHTO T3AT test, and he said they use it and it works. I don't know why in this country it doesn't work. Okay, but it does work in New York City. It works on our jobs, and this is a job that we had with Kiewit. If this test did not work, Kiewit's got some brains in their organization, and they certainly would have put the boots to us, as would have many other people. 20 years we've been doing this test, and people still claim it doesn't work. And we certainly use the Coulomb test for acceptance, the rapid chloride permeability test, and we do that with every sample of concrete. And that's another test people say you can't use it for quality acceptance. Well, why not? We do it every time, every day. And if it doesn't work, then how come somebody didn't come and sue us? We had one guy that threatened to sue us, and then he had second thoughts, and he showed up with his lawyer and admitted that he didn't put the fly ash into the mix, okay, because the Coulomb numbers were so high. So I think those two things are important to do. We need to make sure that we drive the water where it's supposed to be. High water in a mix, more shrinkage potential. High water in a mix, more permeability, you know, and yet we ignore it. We look at a batch ticket and that tells us how much water's in the mix. I'm not accusing anybody of, you know, doctoring the batch ticket, but let's face it, you know, every truck driver thinks that he's a mix expert, and he knows how much more water the mix should have. So if you don't test that load for water content, you don't know how much water's in there. You know, ASTM C94 used to say total water content should be within 3% of the design water. Do they still say that? If that was true, we would never do this test, okay? Because our life experience tells us it ain't that close. We're not doing this for the hell of it. We do this because when we did this test, when we first got this going, we were at 10% over or better in what water was in that truck. That's the reason why we do it. Okay, so let me just, but one thing I want to point out, and I almost forgot the punchline here. We've placed thousands of feet of this, thousands of square feet of this mix. We've walked this, I've walked this with the head of QC for Kiewit, Larry Cochran, maybe some of you people know it. We couldn't find a crack on this deck. I mean, it hasn't been loaded yet, and I'm not saying there's not a crack there, but walking on that deck, you cannot find a crack. I think that thing to say that, you know, here we placed the deck, thousands of square feet, and not a crack did we find yet. I'm sure when we load it, we'll get a crack, but there was no crack visible to us. I'm sure if we got on our knees, we'd find some, okay? But that's how good this mix turned out. And I think that's a success story. Low diffusion characteristics, no cracking, and the strength went along for the ride. We have too much emphasis here on strength and not the properties that really matter. Whether that concrete is 8,000 or 5,000, nobody would miss it. But if you've got a lot of cracks in it, you're going to have poor durability, poor service life in that concrete. And of course, if the diffusion is high, that's not going to work either. So here it is. This concrete couldn't be pumped. Here it is. It's pumped. All of it was pumped. There it is being placed on the deck. And it finished very well. Finishability wasn't an issue, but I got to hand it to Kiewit. They did a great job in doing a mock-up and working out the kinks. They're a great contractor. And here's our curing method. We put the curing membrane down first. As soon as the sheen has left the surface, we want the curing membrane put down. And the curing membrane, acceptance is the entire surface has to be white, just as you're seeing in this slide. And then once we get final set and we can walk on it without marring it, then we lollygag and put the water curing on there. I'm not sure how important this water curing is anyway, but we did water cure it. Okay, the other job I'd just like to share with you is we reconstructed now 2 runways at JFK. And the reason why we've used concrete is because the managers of the airport got fed up with repaving with asphalt. And the driver was the quality of some of the taxiways we built out there, that they had no maintenance issues with them. They wanted concrete. We said to them, we're going to give you a cost benefit analysis of asphalt versus concrete. And the manager of the airport said, don't waste your time. I'm not interested in asphalt. I'm not here to repair pavements. So the point I'm trying to make, if we do quality work, people want it, especially for airports, okay? This runway is almost 3 miles long. It's the longest runway that we have in our system. And 250,000 yards of concrete were placed, and quite a bit of asphalt too. And here again, we have to abide sort of by the FAA spec. But I met with the FAA and said, listen, we want to take some exceptions to your specification. And they were about 2 pages long, because we don't think what you've got there meets our requirements. So, water cement ratio less than 0.45, that's industry standard. There's nothing peculiar about that. Low cement content. The reason why we said maximum cement content, because there's a trend to put in more cementitious material than you need. Okay, for whatever reason, I don't know. It must be very cheap out there. So, we wanted a green concrete. And green concrete doesn't mean that you put in 40% slag and put a hell of a lot of cement in there. Green concrete means you minimize how much cement you have in there. So that's why we put in there maximum 350 pounds of cement, maximum cementitious content 550, which we don't even need, okay, if this thing was done right with the right aggregate gradation. But we cut them a little slack. And here we go. Substitution for supplementary cementitious material. For bridge decks, we say we want fly ash. For pavements, we want slag, okay, because we get great results with the slag. and because of the control joints, we don't get cracking, okay? So here we mandate slag. Total aggregate content more than 70%, and we want large stone in the mixes. This is always a point of contention with the contractors and the concrete producers. They don't want to do this. So you talk about performance-based specifications. What would we get if we didn't insist on this? Why do we insist on 2-inch stone or better? Because we produce concrete that doesn't have cracks in it. Would we get this otherwise? I doubt it. I seriously doubt it. So again, here are our requirements for the aggregate, cost and some workability factors, but we're willing to listen. But we do have requirements or specifications to push this up to have a lot of coarse aggregate and large stone in the mix. We also met with the FAA, and we also told them, listen, we don't think that this makes sense, that you're going to give a bonus. We're going to give a bonus of 6% if we get a flexural strength modulus of rupture greater than 700 psi. We don't think that's worth much at all. We don't think getting 700 psi is an accomplishment if the durability is not in the concrete. Who cares whether it's 750, 850, 950, 1050? If you got a lot of cracks, if you got a lot of spalling, we don't think the contractor should be given a bonus. So we said, look, we think that the water content must be where it was supposed to be by mix design, and that will be confirmed with the microwave test. And the air has to be where it was specified. And the other thing we added in there was the rapid chloride permeability test for one reason only, just to make sure that the pozzolan was in the mix, okay, and that it wasn't left out by accident. So that's why we have that in. And again, to have pavements with low permeability, that's not a bad deal. It's not as important as for a bridge deck, okay? But we wanted to make sure that the pozzolan got in there. It gives you protection in the event that maybe you got some aggregate in there that's reactive. If you have 40% slag, 30% fly ash in there, it's not going to be as reactive, and you're not going to get runways that blow apart in 7 or 8 years, as some of us have heard is happening in other parts of the country. Okay. So anyway, the FAA said that's not fair. They made a deal with the, I guess, Portland Cement Paving Association that if you got over 700 flex, you'll get a 6% bonus. Well, we said, well, we don't want to do that. We're not going to give them a bonus unless the water, the air, and the durability is where we want it. We're not going to give them a bonus. So they reluctantly agreed to it. And they said, well, you're raising the bar too high. So here were the results from that job. The contractor got over $1 million in bonus money. No lot of material didn't meet the 700 psi criteria. 83% of the lots got a bonus, even by requiring that the air, the water, and the diffusion has to be where we specify. 83% of the lots. You know, so the point I'd like to make is that, you know, we need to raise the bar. You know, we need to raise the bar. And look, if we accept material that's marginal, that's what they're going to give you. They're not going to, no one's going to pick the bar up on their own. If you don't pick up the bar, no one's picking it up for you. So this is what we got. The FAA saw our data and they said, you know, we need to get together. I said, what do we need to get together about? You know, we've seen a lot of your data. You keep getting 1,000, 1,100 flex. I said, yeah. Well, you know, if we could do that, if we could somehow repeat that across the country, we could reduce the thickness of the pavements by probably 30%. I said, okay, whenever you want to get together, I'm available. I'm sure I'll be retired before we get together, but it's a good idea. Okay, again, I want to just emphasize that we do check the water content of the concrete delivered. We do that on bridge decks, and we do that for our pavement concrete. Now, the other, and here we go, there's a microwave oven with a generator in the field, and of course it is cumbersome. It does take some time. But again, if we're going to be rebuilding our infrastructure, we should try to do it right. Doing the slump test doesn't quite cut it. I mean, you could take the slump test and sit on that cone as far as I'm concerned, and never do that test. Would never bother me one bit. It's a worthless test, I think. And we added one more requirement to the FAA. We said, you know, your 20 by 20 for control joints, we don't like that either. We're going to go to 25 and 25. And we're going to add another caveat to that. If any of the concrete cracks before we load it, we're putting in our spec, the contractor's replacing it at his cost. And they said, wow, my goodness gracious, how could you do something like that? Well, just watch. Here's the way you put the words in the spec. And we did. We did that. And you know what? It turned out very good. There was roughly 6,000 slabs for that runway, 25 by 25. Only 31 were removed because of cracking prior to opening. 31. Almost half of those were in one night's work where they forgot to cut the control joints. If you don't cut the control joints quickly, you're going to get cracks. Okay? So the moral of the story here is we kept the water down, we kept the aggregate large, we maximized the aggregate, we minimized cracking. Okay? You know, I gave a little talk in Milwaukee, and there was a young engineer there from the FHWA, and he said that they were awarding a contract, a research contract, to see how we can change our mixes so that we can minimize cracking in slabs 20 by 20. I almost choked. I said, you're spending my money on that crap? You don't know yet how to do that? I mean, it's amazing. We go round and round and round. You know, here we go. You know, we've been doing it now for years, and it's working good. So here we go. This was a real success story. And here's the mix design. And again, we said maximum 550. We got maximum 550. Nobody went any lower. And there's the mix design. And here are the results. Okay, we actually made some cylinders. We made cylinders with the beams. And again, people were saying that making the modules of rupture C78, a lot of variability in that test, So we said, well, let's see how much variability we got there compared to C39. You see those numbers there? Compressive strength for this concrete, now again, this was up to 10% of the concrete had plus 2-inch stone, 7,700 PSI compressive strength. Flexural strength, almost 1,100. Look at the coefficient of variability. It was higher for the C39 test than the C78 test. So what gives here? What gives? How did that happen? Look at the water-cement ratio. Water-cement ratio there is what we got by doing a microwave test. Look at the standard deviation, 0.03. That's not too tough to take, is it? I don't think it is. And the air content and the coulombs, of course, were not an issue. So I think it was a great job. And again, what was interesting here, I think, is that the variability in the C39 test was higher than the C78 test. Okay, some myths in the industry, I think, is that, you know, the C78 test has a lot of variability, not by our testing, unless we're making up numbers, that the AASHTO T318 test is not good. Well, I beg to differ with you. I don't understand how we can be rebuilding our transportation infrastructure and never testing for water content. If you look at 318, durability is tied to water. How do we do this without testing for water? I don't get it. Maybe somebody can explain it to me. There's a lot of good people here. Explain it to me how we do that. The rapid chloride permeability test. If we're looking at diffusion values, how do we not do that test when we're sampling for concrete for bridge decks? How do we just do compressive strength? Who cares? The compressive strength is not a big deal. I mean, if you can't get 5,000 PSI concrete, you might as well hang it up. You saw we got 8,200, and we were looking for 6,000. And that's not unusual for us to get numbers like that. If you control the water, control the air, the numbers go through the roof. Okay, that's our experience. Okay, so I think that's where we need to go, and whether we go or not, who knows. Okay, so here's just some shots from that job. That's the mix. As you can see, it's rather bony. This was slip form for the most part. It was old slip form concrete. And you can see it stands up very nicely. That rock does lock into each other. Just some, and again, all cured, membrane cured, and the membrane works very well, so long as you get it down quick, and the entire surface is white. You certainly don't need to wet cure any of this. We also used the same mix where we had irregular sections. We would add some more high range into the mix, and we would finish it conventionally. So that's the same mix, just with more high range in it. And here's the job, and it turned out very good. And again, I think if we're going to have green concrete, if we really mean that we want green concrete, you need to look at how much water you have in your mix so you drive down the cement factors, okay? If you just liquor up the mix with water, you're not going to drive down the cement factor. And again, we could drive down the cement factor by increasing the aggregate content and having a well-graded aggregate. And I think in both cases, we will decrease the permeability and decrease the potential for cracking. Thank you.
Yeah, I guess. Nice talk, sorry. you looked at the controlling of cracking only from the perspective of the design mix. Was wondering what the reinforcement do in all of that.
I didn't get your question.
I mean, you looked at controlling shrinkage cracking only from the design mix of the concrete.
Yeah.
My question is what the role of the reinforcement plays in all this story. I mean, we know that reinforcement can restrain or even cause shrinkage cracking. What's your thought about that?
Well, for the runway, there was no reinforcing steel.
Well, for the bridge.
Yeah, well, certainly the reinforcing steel certainly helps. No question about it. Keep the cracks tight, if they do develop. If your question is, does the reinforcing steel eliminate cracking? I'm not sure that's true at all. I mean, I've been to many jobs where we had as much reinforcing steel as we had here, and truthfully, the deck looks like somebody dropped it. That's how much cracking was in it. So, and again, it's not just all mixed design. I certainly want to give credit where credit is due. And we did have a good concrete supplier, and we had a very good contractor, and there was good collaboration between everybody. There was much discussion on, we're doing this, we're doing that, how about this, how about that? And that's what made it work. The collaboration between all parties. It's just not mixed design. But if you start out with a lousy mixed design, then you're doomed. I don't think you stand a chance of producing anything that's not going to crack. And we've been down that road before.
Right, thank you.
My question is, you have a very, your whole talk is about actually being quite prescriptive in
Yes.
how you specify your mix, specify your concrete. Where in your experience can you be prescriptive, if any?
Where you can be prescriptive?
In other words, where can you...
Are you talking about performance?
Performance?
Where you can... This is more prescriptive than performance, but it's a combination of both. Again, we do not give... I hide behind, this is a performance-based specification. We don't give the mixed design. Okay, we do not give the mixed design. We set conditions for the mixed design, but we don't give the mixed design. Okay, and again, I think for bridge decks, for concrete used in the transportation infrastructure, I don't think the wherewithal is out there to do it right. I honestly do not believe it. I mean, Kiewit's a good contractor, and Parsons a good consultant. We had a session where Parsons came in and they spoke about this job. And I don't know if you know Bill Phelan, but Bill Phelan was there, and he said to this fellow, Peter Elsner, he says, Peter, the Port Authority had .03 here for shrinkage. What do you typically see on your jobs? He hesitated, and he said, Bill, this is the first time anybody's ever specified shrinkage. We never see it. Which again, it's a sad reflection on how we do business, I think. But where can we have performance? Was that your question?
All I'm saying is that, you've got a lot of specified here. So,
Yeah.
In your opinion, it's important to, maybe you don't give the mixed design, but you're pretty much giving everything else.
For the mixed design, we're giving everything?
Well, you're giving requirements.
Yeah.
Yeah, so essentially you're dictating the mixed design.
Yeah.
Yeah.
But our life experience is that if we don't give that, we get what we refer to as crapcrete.
Yeah, I don't think it's bad. It's just interesting.
So that's why we do this, because if we don't do this, what we get we don't like.
One more question. Different application for more high-rise applications where you're trying to get 10,000, 12,000, 14,000 PSI concrete. What's your experience there?
We've done it. We were involved in the reconstruction of the World Trade Center. We took over the construction of Tower 1. We had 14,000 PSI concrete in there. We got it. So it's doable. In New York City, 12, 14,000 PSI concrete is commonplace. Is it doable? Absolutely, it's doable. And there's a lot of concrete producers in New York City that do a damn good job with high-strength concrete, and they're good at it. So it's definitely doable. No doubt about it. If that's your question, it's doable. Hands down doable in New York City. Absolutely.
You said that your mix design is kind of hybrid between prescriptive versus
Correct.
Performance. So which aspect of your specification is performance? Is it only shrinkage requirements and the permeability, or other aspect that you think?
I would say it's shrinkage. For the bridge deck, it was shrinkage, it was strength, and it was the rapid chloride. Those three.
Do you think
But we wanted the others in there. Fly ash, no silica fume, 1.5 inch aggregate. That we wanted.
Do you think that combined gradation will also help the shrinkage cracking, the cracking on the bridge deck, because you didn't specify the gradation of aggregate. You just specified the maximum size, but the producers seemed like they use combined. So although it was not in the specification, but they use it for the. Could you in your specification to make it more performance or more prescriptive?
Oh, you make a good point. You know, when we started out on the Goethals Bridge, I was told by our chief engineer, we were going to put in there costless workability factors, or the 45 power. If you're talking about blending the aggregates, what we said is 467 stone. Yeah, we did that because people were saying we're putting too much in there. There were people in the Port Authority that walk around with these rose-colored glasses that think that the world is beautiful, and that they said, listen, don't be so prescriptive. What we need to do is open it up and see what the industry will give us, okay, and see what's out there. Well, truthfully, I was very disappointed because what we got was what we were doing 20 years ago. I could honestly say there was nothing new that we got. Okay, so we should have put something in there to better define the aggregate blending, and we will from now on, because it was a war to just get the 467 stone, and it was blended with a number 8 stone. And it could have been done more effectively. If you see there, we had 625 pounds of cementitious material. The strength was 8,200. We didn't need that much paste in there. We could have drove the paste down if we got the better workability out of the aggregates. But the contractor, and he was a good contractor, and the concrete producer were good. They weren't interested in looking into blending aggregates. Are you kidding me? They got too many other things to do to be worried about that. So when we talk about leave it to the industry, let them develop it, where's the incentive for them to develop it? Where's the incentive? They're busy every day shipping out concrete. You think they're going to sit down and try to work out a better blended aggregate for you? There's no way. I don't see it. It doesn't happen in our neck of the woods. Maybe it happens in other parts of the country. It doesn't happen where I work. So you have a good point there, and going forward, we're going to be more prescriptive because nobody really addresses it. You got a question?
I mean, do you feel like there's potential for the contractors in your area to have become accustomed to what you're doing with your prescriptions to eventually turn it into more performance?
I hope so.
You're training essentially, you're training kind of the industry.
I don't know whether it will ever get there. I honestly do not know. Again, everybody's concerned about their problem that day. And who's paying them money to research this? Nobody. They're not going to invest time and money in doing this. And I think that's where I think we sometimes lose track of reality. Who's going to do the research? Nobody.